सुस्वागतम, नमस्कार, केम छो, आदाब, good afternoon, good morning, good evening, depending upon which part of the world you are. आप सभी का PRL के अमृत व्याख्यान में स्वागत है, अभिनंदन है. A very warm welcome from me, Anil Bharadwaj, for PRL का अमृत व्याख्यान. This is the 27th episode of Vyakhyaan of the 75 episode series of Vyakhyans, which is being organized as a part of PRL's 75 years of legacy and history in fundamental physics and space sciences. Established in the year 1947 by the father of Indian space program, Dr. Vyakhyaan, the PRL's Platinum Jubilee coincides with the India's 75 years of independence. So it's a joint celebration of development of science and technology in India by PRL under the banner of PRL ka Amrit Vyakhyaan. Today we have yet another distinguished speaker, Vyakhyaan Karta, Professor Derek Vance from Department of Earth Sciences in ETHA or Federal Institute of Technology in Zurich in Switzerland. Professor Vance is well known to Indian scientific community, particularly geoscience community, and he has visited PRL about 3 years back when he was serving as one of the members of the PRL's decadal review team. So welcome, Derek, to PRL virtually and especially to PRL's Amrit Vyakhyaan. And we are all eager to listen to you. So may I now request my colleague, Dr. Vineet, to formally introduce Dr. Vance. Vineet, please.
Yes, thank you very much, Professor Bharadwaj. It is indeed a pleasure and honor to introduce today's speaker, Professor Derek Vance. He is currently working as a professor of geochemistry in the Department of Earth Sciences at ETH Zurich, Switzerland. In the past, he has worked on mental geochemistry and has used geochronology and metamorphic petrology to understand mountain beds such as in the Alps and Himalaya. For the past 10 to 15 years, however, he has focused on understanding the geochemistry of the Earth surface processes. This has involved the quantification of the global cycles of trace elements through investigations of their inputs to the dissolved pool of the ocean and outputs to various kinds of sediments. An important long-term objective is to use this effort targeted at understanding modern budgets to understand the chemical evolution of the surface Earth in the past. His research has contributed significantly to understanding the geochemistry of the non-traditional metal-stable isotopes. Professor Vance obtained his PhD in geochemistry at the University of Cambridge, UK. He has served as a co-editor-in-chief for Earth and Planetary Science Letters, as an editor of Geochemistry, Geophysics, Geosystems, and as an associate editor for Geochemical at Cosmochemica Acta. So all of them are very reputed journals in geochemistry. He is currently the president of the European Association of Geochemistry and head of Earth Sciences at ETH Zurich. In 2019, he also served on the PRL Decadal Review panel. With these words, I would now like to hand over the stage to Professor Derek Vance and invite him to deliver his talk. Thank you very much.
Thank you, Vineet. And thank you for the invitation. It's a pleasure to do this. I wish I could be with you instead of doing this online. As you said, I was there 3 years ago and had a fantastic time. And congratulations on your 75th anniversary and all the great work that the PRL has done over that time period. It's a real pleasure to be able to mark that with you. So I will share my screen and get started. So you can all see that?
Yes.
Okay. So I'm going to talk today about in the end today, I'm going to talk about the ocean geochemistry of transition metals. But before I start, I would just like to make sure that you all realize that, well, I've been head of department for 3 years and haven't done much research in that time period. So a lot of what I'm going to say today is the work of students and postdocs, which I will mention a little bit as we go through the talk, but here are some of those people, just so that you can see who they are and put names to faces later. So today, because I have been at the PRL, I know that there are many things, many groups, and there are many people doing different things in different aspects of Earth and planetary science at the PRL. So I thought it would be wise today to at least start my talk broadly and to draw some of the non-geochemists into what I'm going to say before I get into the details of what we do a bit later. So I'm going to start actually by, on a fairly large scale, by talking about what we know about the progressive oxygenation of surface Earth. And one thing I'm going to emphasize is that this progressive oxygenation of the surface planet is an important planetary scale process. Another thing I'm going to emphasize is that it's very intimately linked to the evolution of the biosphere. So that's where I'll start, and that will be really background information. And then I'm going to tell you something about how geochemists try and quantify, understand that history, how we know about that history, how we know about how the Earth has progressively been oxygenated at its surface. And you'll see that this information comes from the rock record, and most directly, it comes from the investigation of redox couples and how they operate in the ocean and atmosphere, and how the information on them is preserved in sediments in the ocean. So this is all going to be more or less background. It'll be the first half or first third of the talk maybe. And then at the end, I will get to the things that I do and that we do in our group, which will focus in a little bit on a more indirect way of understanding the past oxygenation of the surface Earth using trace metal isotopes. This is really my business. And I will also focus in on the ocean, and particularly on the Phanerozoic ocean, so the last 500 million years of Earth history. And you'll see that these things are potentially powerful, but there are also some things that we don't understand properly yet. And my main point at the end is going to be, if we could understand them a bit better than we do currently, we could really use them in a much more powerful way to understand this important aspect of Earth history. So this is a fairly famous diagram now. It comes from a Nature paper a few years ago by Tim Lyons. And what it shows is what we think we know about the oxygenation history of Earth's atmosphere. All right, so we have time along the x-axis here, going back to 4 billion years ago to the present day. And then the scale on the left here shows the partial pressure of the molecule O2 in the Earth's atmosphere. And the scale on the right is just the same thing, but the amount of oxygen is normalized to the present day level. So 1 here is the present day level. And what this history shows, it's an outline history. We don't know a lot of the details here. What it shows is that the history of O2 in the Earth's atmosphere has been one of long periods of stasis, of stability, nothing much happening, and then shorter periods of time when things have changed rapidly. So, for example, we know that for about the first half of Earth history, the Earth's atmosphere contained virtually no oxygen. We only have a maximum limit on how much oxygen there was in the atmosphere during this period, but it was probably somewhere, well, it was definitely beneath 10 to the minus 5 modern levels of oxygen, and perhaps way, way beneath that. All right, so we started with an Earth in which the atmosphere was virtually anoxic. But then the first thing that really changed was around here, about 2.4 billion years ago, when something called the Great Oxidation event happened, when there was a rise. To what level, we are not entirely sure, but it definitely rose above this previous maximum of 10 to the minus 5 modern levels. And it may have stayed high, it may have gone back down again. The other thing that we're fairly certain of is that after another long period of stability, maybe 1.5 billion years here, there was a second rise, maybe something like 500 or 600 million years ago. And since about that time, it has been close to modern levels, at least the same order of magnitude as modern levels. It may have gone up and down a little bit. It probably did go up and down a little bit over this time period, but it was relatively high. Now, this great oxidation event has been a subject of intense research. What caused it, and what was its nature? And there's still a big debate about what caused it, or at least what I'm going to call the proximate cause of it. So in order for this to happen, in order for molecular O2 to increase in the Earth's atmosphere, you need to do one of two things. You need to decrease the sink of oxygen, what's taking oxygen out of the atmosphere, or you need to increase the source. And as I say, there's still some debate about which one of these two actually caused the GOE to happen when it did. So, for example, there's a school of thought that this happened when it did because the flux of reductants from the hot interior Earth decreased at this time. In other words, the material that takes oxygen out of the atmosphere by reaction with reductants decreased at this time. And that's a possibility that is the cause of that increase at this time. But one thing is for sure, one thing that you absolutely need before the GOE, regardless of whether the sink went down at this point, is that you need a source of molecular O2. And the only significant source of molecular O2, way bigger than any other source today, is this thing, oxygenic photosynthesis. And that's the metabolism that plants use, written in a very simple form here. They take CO2 out of the atmosphere, they react it with water, they split the water, they combine the hydrogen with CO2 to reduce that carbon to make their cellular organic material, and O2 is produced as a waste product. And whether the sink went down at this point, and whether this was the proximate cause of the GOE, you definitely had to have this metabolism there before the GOE. You had to have a source. And there's a debate about when oxygenic photosynthesis evolved and whether it evolved way back here and oxygen levels in the atmosphere were kept low because of the flux of reductants from the mantle, or whether photosynthesis evolved just before the GOE. Okay. Whatever happened here, this was a major change in the Earth's atmosphere. Of course, it led to the development of a UV shield on planet Earth. Molecular oxygen itself filters out UV light, and of course, ozone, which is a product of O2 made in the stratosphere, also filters out UV light. So this was important to the further development of life on the planet. And then the other thing that's sort of intriguing is that the first time we see complex multicellular animal life on Earth is about here, about 500 or 600 million years ago. And this occurred when, well, close to the time when the second rise of molecular oxygen happened in the atmosphere. And of course, all animal life needs oxygen. You and I do. It's what we use. The oxidative power of O2 is what we use to oxidize organic matter, thereby releasing the energy in that organic matter, which then is used for our metabolisms. So the thing I want to point out here is this history of oxygen in the atmosphere is intimately connected with life in two ways. First of all, this thing here, the evolution of oxygenic photosynthesis, caused O2 to rise in the first place. And it was only that rise that led to other things that are really important to the subsequent development of life on the planet. And there are other links too. So this reaction produces O2, this oxygenic photosynthesis reaction produces O2. But if that's all that happens, then this reaction will be reversed. There will be something that will respire that organic matter, reuse the O2. And what you need to do with this organic matter is get it away from the surface of the Earth before the reverse reaction can happen. And that happens on Earth because that organic carbon is buried in rocks. And that burial of organic carbon in rocks also removes CO2 from the atmosphere. And it is burial of organic carbon that is one of the main controls on how much of this important greenhouse gas there is in the atmosphere as well. So that's another link with the evolution of the Earth in general and with biology. And we can look at this burial of organic carbon using, for example, carbon isotopes. So when photosynthesis happens, it preferentially uses the light isotopes of carbon. And so when you get pulses of organic matter burial, you get the atmosphere and oceans becoming heavier in carbon isotopes because the organic matter is removing the light isotope. And so the history of oxygen is tied up also with the history of carbon isotopes in the ocean atmosphere system, as shown here by this black curve. I'm not going to talk about these orange points. These are mass-independent sulfur isotopes. They also tell us about the oxygenation history of the Earth, and they are actually the firmest evidence we have now for the GOE, the most quantitative evidence we have for the GOE, the fact that these mass-independent fractionations of sulfur, which I'm not going to go into the detail of, disappear here at about 2.4 billion years ago. And so for the planetary scientists in the audience, and this is something I've been talking about a lot with colleagues here at ETH recently, of course, all this atmospheric chemistry is observable from space. And there's an increasing interest in exoplanets and the chemical compositions of their atmosphere. And if we were to look at Earth, we would see aspects of the atmosphere that can only really be caused by life. Not in a simple way, but for example, just to give you one example, the fact that the Earth's atmosphere has ozone and methane as well is really an indication that the Earth is living, because ozone and methane can be produced independently of each other, but they're really unstable in the atmosphere together. They should not be in an atmosphere together. There has to be a source of them that is operating there all the time, and that source is to do with life on Earth. Okay, so that was a sort of potted history of atmospheric oxygenation. What I want to do now in the second part of the talk is just tell you a little bit about how geochemists have understood and quantified that history. How do we know what we know? And this is all about the rock record. We get this information on the past Earth from the rock record. And in particular, what we use here are redox couples. So just to give you an example, to make that a bit more concrete, what this diagram shows is where elements change their redox state as a function of the overall oxidizing or reducing conditions that they experience. So as an example, here's one of those redox couples, iron 2 and iron 3. Iron at the surface of the Earth has 2 valent states. It can be iron 2+, or it can have another electron stripped away and become iron 3+. And one question that geochemists ask is, when did conditions at the surface of the Earth become oxidizing enough for iron in its reduced form to be transformed into iron in its oxidized form? When was the surface Earth oxidizing enough for that transformation to happen? And so these 2 redox couples here tell us about the transformation towards more oxidizing conditions when conditions are still pretty reducing. Today, the oceans and atmosphere are, of course, way up here, much more oxidizing than these 2 things, up here where we have much more oxidizing conditions like in today's atmosphere and ocean. So how do we use these things? Well, here's one example. So taking iron as an example, this is a picture of a soil, or actually it's a picture of 2 basaltic flows on the island of Hawaii. And there's a more recent flow on top here, on top of an older flow. And the older flow has had a soil developed on it. And that soil is red. And it's red because when this basalt weathers, when it gets attacked by rain and atmospheric CO2 dissolved in that rain, making the rainwater slightly acidic, it chemically weathers. And the minerals break down and release their iron. And the iron in those minerals is predominantly in the 2+ form. But when that iron is released under our currently oxic atmosphere, it transforms to iron 3. So the soil is rusty looking. It's full of iron 3, iron oxide. And so under an oxic atmosphere, if you look at a soil profile of iron concentrations, what you see is that as you come towards the weathered surface of the soil, iron 2 decreases in abundance because you are breaking down the minerals that contain iron 2, but you do not lose iron from the soil. The iron that's released from the minerals is kept in the soil because it's transformed to iron 3. by the oxic power of the atmosphere, and iron 3 is insoluble. It is not washed out of the soil by the aqueous solution of groundwater and into rivers. It remains in the soil as a solid secondary iron oxide mineral. It is not lost. And this is a consequence of the fact that our atmosphere is oxic. In an anoxic atmosphere, we would expect to see something different. We would expect to see the iron 2 that's released from the minerals staying in aqueous solution and being washed out of the soil into rivers and into the oceans. And we would expect to see iron concentration decrease to low concentrations at the top of the soil where the weathering is most intense. And people have used this to try and understand the history of oxygen in the atmosphere. They've looked at paleosols, ancient soils preserved in the rock record, and they've looked at how iron behaves in those soils to see whether it looks like this or whether it looks like this. When you try to do this in a quantitative way, and in ways that I'm not going to go into here, there are quantitative ways you can use this to get upper and lower constraints on the amount of oxygen in the atmosphere. If you're lucky, you get both an upper and a lower constraint on oxygen in the contemporary atmosphere when that paleosol formed. Mostly, though, you either get maximum constraints or minimum constraints. However, this is one way in which people have tried to understand the oxygenation state of the atmosphere by looking at whether iron is lost from soils. If it is, we must have had an anoxic atmosphere, or to what extent it's retained. And as I say, you can in principle get quantitative information as is shown on here. Another really important observation is this. So because of the fact that iron on the oxic earth is not soluble in solution because it's transformed to the oxidized form, which precipitates out of solution. For example, modern lakes, rivers, and modern oceans contain tiny, tiny amounts of iron. So iron is an abundant element in the continental crust, and you might expect it to be abundant in solution in the oceans, but it's not. It's present at absolutely tiny levels in solution in the modern oceans. It's present at nanomolar levels. And the reason is that the soluble form of iron, iron 2, is not stable at the oxic surface of the modern Earth. It's quickly transformed to iron 3, and it stays in soils. It's not washed into rivers, not washed into the oceans. It's precipitated very close to hydrothermal systems, so it doesn't get into the open ocean. And this apparently was not true on the early Earth, because on the early Earth, over the first roughly 2 billion years of Earth history, we apparently had a lot of iron in solution in the oceans, perhaps 10 to the 5 times more than this very low modern level. And we could only have had that, and we know this because we get these banded iron formations in the rock record in the first half of Earth history. These are rocks that formed as chemical sediments in the ancient oceans. They are formed by the precipitation of iron from a solution that must have been rich in iron, and it could only have been rich in iron if the iron was in the iron 2 form, the soluble form. They're common in the first half of Earth history, and then they stop. They stop. There's a last pulse at about 1.9 billion years ago, and then they stop. And so making one of these banded iron formation requires an ocean that has huge amounts of dissolved iron in it, not like the modern ocean where dissolved iron is tiny in abundance because iron is not stable in solution because it's not in the iron 2 form. Whereas this Archean ocean, these early oceans were apparently what we call ferruginous. They were rich in iron. Now, another thing that probably happened at the GOE when the atmosphere became oxidizing is that you started to weather rocks at the surface of the Earth oxidatively. Now, one important consequence of that is this reaction here. So this shows pyrite, which is a common mineral in many rocks on the continents. Today, it weathers by reaction with oxygen to produce iron, which precipitates as iron 2 and is left in the soil. But another important consequence is that you make sulfate, and that sulfate is soluble and is washed into the ocean. So a key observation about the GOE is that before it, you contain, such as this example from South Africa, the rocks contain detrital pyrite. This is pyrite. It's clearly pyrite, and it's been rounded. It's been transported in a river at the Earth's surface, and yet it has not oxidized. It has not weathered according to what this reaction says it should. It does not look like weathered pyrite like this with rust on its surface. So what this is telling us again is that the atmosphere must have been anoxic before the GOE. Otherwise, this detrital pyrite ought to have gone through this reaction as it was carried from the source rock in the river and into this conglomerate where we find it now. But just to go back, the important consequence here for me is that you produce lots of sulfate, which is washed into the ocean. And people have suggested that what that did then is triggered bacterial sulfate reduction in the ocean. So this is another respirative metabolism, probably more important before the development of oxygen, by which organic matter is broken down by reaction with sulfate as the oxidant, not oxygen, but sulfate as the oxygen, to produce hydrogen sulfide. And this equilibrium causes a big isotope fractionation in sulfur isotopes, mass-dependent fractionation. And we know this started to happen at the GOE. There was this transformation occurring because the record is preserved in sulfur isotopes in the rock record. So what this diagram shows is the isotopic composition of sulfur in pyrite, in sulfides, the gray points here, and in sulfate, preserved in evaporitic rocks now. And what you see is the isotope composition of the sulfide and the sulfate are different. And this is because of this reaction, the bacterial sulfate reduction, which strongly prefers the light isotope in the H2S phase, and that H2S then goes on to react with iron to make pyrite, and that's what we see in these light isotopes. Now, this idea has led people to propose that in terms of the oxygenation of the oceans, what happened was maybe something like this in broad scale, that we started in the Archean with an ocean that was anoxic, as I've just said, because the atmosphere was anoxic. Because it was anoxic, it was iron rich, because we had iron 2 in solution. Today, we have an oxic ocean, which is iron poor, because iron is not stable in solution in the 3+ form. But we might have gone through an intermediate stage in the Proterozoic between this early and this present state, when the ocean was full of sulfide, because by this time we had an oxic we had some oxygen in the atmosphere, we had oxidative weathering of pyrite supplying sulfate to the ocean, triggering sulfate reduction, producing sulfide. We might have had a sulfidic ocean, and that ocean would also have been iron poor, not because it's oxic, but iron poor because sulfide and iron in solution are completely incompatible. You only need tiny amounts of each and they will precipitate as an iron sulfide. And so this has been suggested as a general history of the oxygenation state of the ocean. And this is important because the Proterozoic is this long period of time when nothing much happened in terms of oxygenation of the Earth and nothing much happened in terms of the biosphere. It's been termed the boring billion in terms of Earth history. And this may be because we had a sulfidic ocean, which is not a friendly ocean for life. Okay, so now I'm going to focus in on this period of time, on the Phanerozoic, because we're going to see in a minute that things continue to happen. The oxygenation state of the surface Earth continued to change during this Phanerozoic, and I want to go into that in a bit more detail. So what I've been telling you about mostly so far, what this diagram summarizes, is an outline history of O2 abundance in the atmosphere. What I'm going to narrow in on more now is O2 in the ocean. I've just talked a little bit about the oxygenation state of the ocean, but I want to focus in more on that now. And what has become clear, particularly recently, is that the oxygenation of the interior, the deep ocean, is not simply related to the atmosphere. There's increasing signs that the ocean became oxygenated later than the atmosphere. Surface ocean, not. The surface ocean is in chemical equilibrium with the atmosphere and probably was oxidizing as long as the atmosphere was oxidizing. But it's become increasingly clear that that transfer of oxygen to the deep ocean happened later. Why would that be? And so what I'm going to do in the next few slides is just focus in on what controls oxygen in the interior ocean today, because that will set the scene for what I want to say in a minute. So the modern ocean is virtually never anoxic, at least in the open ocean, even at depth. It gets close in places, but in general terms, it is oxygen levels are never zero in the modern deep ocean, but it gets close. There are places, though, in marginal basins where it is anoxic in the deep sea. And the famous example of this is the modern Black Sea. So the modern Black Sea is an isolated basin. It's fed by water inflow at depth from the Mediterranean. But the characteristic of the Black Sea that's important here is that there's a lot of rivers and fresh water coming into the Black Sea. Its salinity is low at the surface, and therefore it is stratified. There is not much water sinking from the surface into the deep Black Sea. And therefore, there is not much atmosphere equilibrated O2-rich water sinking to depth. And as a result of that, O2 quickly runs out in the deep Black Sea, and the deep Black Sea becomes sulfidic instead. Now, it goes through an interval where iron is soluble, just like the Archean Ocean. Here, when sulfide is not too high and oxygen is already low, but that's very thin because it quickly becomes sulfidic, and then iron and sulfide precipitate together as sulfide minerals. So what we're seeing in the Black Sea is sort of a recapitulation with depth, as a recapitulation of Earth history, in that we have an oxic surface, we have an iron-rich middle here, but as soon as it becomes sulfidic, iron concentrations go down. So that's the source of O2 to the deep ocean. It comes from atmosphere equilibrated surface water, and then the physical circulation brings that oxygen-rich water down into the deep ocean. That process is temperature dependent because the Henry's law constant that determines how the atmosphere equilibrates with the ocean is temperature dependent. So oxygen is much less soluble in warm water than it is in cold water. So there is a temperature dependence of that surface source of oxygen to the deep ocean. But the other thing that's important here is the sink of oxygen in the deep ocean. And the main sink in the deep ocean is aerobic respiration. Again, this is what you do, but most importantly in the ocean is what bacteria do. Bacteria react organic matter with oxygen to consume it. And as you guys know, I know you work in the Arabian Sea, some of you, there's an oxygen minimum zone in the middle of the ocean often where respirative consumption of organic matter coming down from the photic zone is at its maximum. And that interior ocean sink is controlled by the amount of photosynthesis in the surface, because that's the source of the food the bacteria respire with oxygen, right? That's the source of the food. So it depends on primary productivity in the surface ocean. And it also depends on the degree of export of that organic material into the deep ocean, because it's in the deep ocean where the oxygen is being mostly consumed by aerobic respiration. And so there are increasing indications that these processes that control the oxygenation of the deep ocean were important and kept the ocean anoxic quite some time after the atmosphere had become oxic. And so, for example, this is the result of a compilation of lots of sedimentary iron speciation data. Again, it's using this redox couple and how information on that redox couple is preserved in ocean sediments. And its suggesting, for example, that at least the deep ocean was oxygenated quite late, maybe into the late Paleozoic, before the deep ocean left this anoxic state. There are many more indications of this, a lot of work going on. This is another piece of evidence. What these guys did was to look at the oxidation state of iron in hydrothermally altered oceanic basalt, with the logic that the hydrothermal fluids that alter oceanic basalt are derived ultimately from the ocean. So if they're oxidizing, we would expect the oxidation state of iron in the altered basalts to be oxidized. If they're reducing, we would expect the iron to be reduced. And these guys suggest that the deep ocean, again, did not emerge from anoxia until really quite late, maybe even halfway through, maybe even the latter part of the Phanerozoic. So only in the last few 100 million years. there's a big error bars on this conclusion, but that's the suggestion that they make, that the deep oceans emerged from anoxia really quite much later than we might once have thought. The other piece of evidence for this goes to another one of these redox couples. So iodine is a thing that's being increasingly used. Iodine is transformed from the iodate species to the iodide species at very oxidizing conditions. So iodate is the oxidized form, iodide is the reduced form. Now, iodate goes into carbonate. Iodide does not. So when the iodine in the ocean is in the iodate form, we would expect to find lots of iodine in carbonates. It substitutes for the carbonate anion in carbonate. So people have started to look at iodine-calcium ratios in marine carbonate through time. Again, remember, the logic is that if iodine is in the iodate form, it will go into carbonate. If it's in the iodide form, it won't. And what they see, again, is changes really late in the Phanerozoic. There's possibly an oxidation event here around 400 million years ago, but right up until the present day, or at least right up until the last 100 million years, iodine-calcium ratios in marine carbonate are changing, suggesting that there's some movement in the amount of iodate in the ocean relative to iodide. And again, this must be caused by oxygenation of the ocean. And these guys in particular have suggested, the guys who work on iodine calcium, they have suggested that the reason this might be happening is not to do with how much oxygen there is in the atmosphere. It's not to do with how well oxygenated the surface ocean is, which is in equilibrium with the atmosphere. It may be more to do with the nature of the biological pump, the process by which reduced organic carbon is exported from the surface ocean and into the deep ocean. And it's possible that that biological pump, which transfers the reducing material into the deep ocean, where it can be respired and therefore consume oxygen, maybe it changed. Maybe it changed in response to the evolution of larger phytoplankton, which fall into the deep ocean more readily than smaller ones. And it is true, just to finish this background section, it is true that the ocean's carbon cycle and oxidation state has continued to be very dynamic and very turbulent all the way through the Mesozoic. So people often talk about these mass extinctions. There have been 5 of them in Earth history. The last one was back here at the Triassic, well, no, the last one was at the Cretaceous Paleogene boundary. A lot of these are associated with oceanic anoxia. A lot of them are associated with warm periods. A lot of them are associated with pulses of organic carbon burial. And so there are indications that the ocean maintained its dynamism in terms of its redox state for a lot longer than you might think if you were just looking at the atmosphere. Okay, so now then for the second half of the talk, I want to focus in on what we do. And what I want to say at the beginning, and this is a take-home message actually from the rest of the talk, is that there's another redox couple here that we can use to study this kind of thing in the ocean. And it's the redox couple between manganese 2+ and manganese 4+. And it behaves a lot like iron. The reduced form of manganese is soluble in an aqueous solution. The oxidized form is not. And so when the oceans became oxidizing enough that manganese was predominantly in the 4+ form, you would start to form solid manganese oxides, which would be buried in sediment, and that has consequences for trace metal isotopes that I want to go through. But I want to also stress that there are some things I'm going to present at the end. I'm going to present some puzzles actually in this field that suggest that our understanding of some of the things I'm going to tell you about is not complete. And if we could understand them better, we could use these trace metal isotopes in a much better way. So I'm going to start with something that I know is familiar to some of you, and that's the element molybdenum, which is a second row transition metal, and it's got some very interesting features that are relevant to what I'm talking about today. So this shows a pH, EH diagram for the system molybdenum, water, H2S. And what I want to stress here is that molybdenum is not a redox sensitive element at the surface of the Earth. It does not change its valence state, at least under normal Earth surface conditions. It's always in the 6+ state, right? But there's something important that happens that is related to the oxidation state of the surface Earth, as you'll see. So in today's open ocean, which is well oxidized, molybdenum exists as this oxyanion, the molybdate ion. And that's the common form of molybdenum in today's ocean. When you get, though, to sulfidic conditions, right, when sulfate is transformed to reduced forms of sulfur, then molybdenum's behavior changes. It is transformed from a molybdate into something called a thiomolybdate. It's a sulfidate. The oxygens are replaced by sulfur. And this is important because even though molybdenum maintains its oxidation state here, it's always molybdenum 6+, this molybdate ion is really soluble in the oceans. The thiomolybdate is not at all soluble, as we'll see. So one of the remarkable things about molybdenum is because it forms this very stable, very inert molybdate ion under oxic conditions in the open ocean. It's got a very long residence time and is very abundant in modern oceans. So one of the truly remarkable, I always tell my students this is truly remarkable. Molybdenum has a concentration in the continental crust of 1 ppm, many orders of magnitude less than the concentration of iron, for example. And yet, because of its solubility in aqueous solution, its concentration in today's ocean is orders of magnitude greater than iron, 2 orders of magnitude greater than iron, even though its abundance on Earth in general is much less than iron. And I find that, a really interesting and remarkable thing. So there's lots of molybdate in the open ocean. Okay, so I'm going to talk about molybdenum isotopes in a minute. So this is a stable isotope system. There are many isotopes of molybdenum, but the fractionations that we see in molybdenum, the ones I'm going to be talking about anyway, are mass dependent. So I'm going to be talking about these mass dependent isotope fractionations in the usual way. I'm going to be talking about delta 98 molybdenum, which is the stable isotope ratio of molybdenum, the 98-95 ratio, normalized to a standard and expressed in per mil deviations in the usual way. So if we look at the modern oceans, what we see is that molybdenum is a conservative element. Its concentration in the oceans is really high. If you go to different parts of the ocean, you get the same concentrations, roughly 100 nanomolar, almost everywhere in the open ocean. If you measure the isotope composition of molybdenum, it's also constant and uniform in the open ocean. It's about plus 2.3 per mil in this delta 98 molybdenum scale. And that's interesting for a start, because that is not the same as rocks on the continent. Rocks on the continent are about 0 per mil in terms of delta 98 molybdenum. And the main source of molybdenum to the oceans, rivers, which we measured a long time ago now, are down here at this isotope composition. So how can the main source of molybdenum be this isotope composition, and the composition of the oceans themselves be here? And the reason is that there's an output flux from the oceans. It's molybdenum associated with manganese oxides in the oxic open ocean that preferentially removes the light isotope, therefore making the dissolved pool heavy relative to the input. And the nice thing about molybdenum is that when people have done experiments to see what isotope fractionation you get when you absorb molybdenum to manganese oxides, you find that it's exactly the same as the difference that we measure between the modern ocean and manganese oxides, or almost exactly the same. So that's nice. So we have molybdenum removed from solution very slowly by absorption to manganese oxides with a big isotope fractionation that makes the modern oceans heavy relative to the input. Now, when you go to the Black Sea, which is sulfidic, you see something completely different. So in the deep sulfidic Black Sea, molybdenum concentration are not constant, and they go to very low values. And the reason is that in the deep Black Sea, the molybdate ion is being transformed to this thiomolybdate ion, the sulfidized ion, which is very insoluble and very quickly removed from solution. So two important aspects of the modern budget of molybdenum are shown on this diagram. And what I'm trying to do here is also, by the way, explain the record of molybdenum concentrations in sediments through Earth history from 3 billion years ago to the present day. So what you see here on this diagram showing the molybdenum concentration of sediments is the early rock record has very low concentrations of molybdenum. And that's probably because the ocean didn't have much molybdenum. Molybdenum in the continental crust is mostly in sulfides. You didn't have an oxic atmosphere back here, so you didn't have oxidative weathering of sulfides. The source of molybdenum to the ocean was very small, so concentrations were small. When we get to this point here in the Phanerozoic, the last 500 million years or so, it's very different. Now we have a fully oxic atmosphere. There's a strong source of molybdenum from oxidative weathering. We have an open ocean probably for most of this time, which is oxic. We have a molybdate ion, which is very stable, lingers a long time in solution, allows oceanic dissolved concentrations to get very high. We have an output in the open ocean by absorption to manganese oxides, but that output is very slow. And even though it happens, the sediments in the open ocean do not contain much molybdenum. However, the other thing that happens is that we have marginal basins like the modern Black Sea. And we have water exchange between the open ocean and these marginal basins. And the water coming in brings in a load of molybdate because the open ocean is oxic. But when that water gets into the Black Sea, it gets sulfidized and removed from solution. And so sediments in places like the Black Sea are very rich in molybdenum, but they're rich because they're fed by the open ocean with this water that's rich in molybdenum, and then it's removed very efficiently by the transformation to sulfide. So for example, in the Phanerozoic, you see a big variation in sedimentary concentrations of molybdenum because you're looking at sediments that were made out here, but you're also looking at sediments that were made in here. The important point is that it can get very high, the concentrations of molybdenum, because you do have an open ocean that's got lots of molybdenum, and if you feed it into one of these basins, they can remove it, and they have sediments that are very rich in molybdenum. So again, focusing in on the Black Sea, the other thing that happens in the Black Sea is to do with the isotopes. So now, if you looked at sediments out here, as I've just told you earlier, the molybdenum in them will be very isotopically light because it's mostly manganese oxide associated molybdenum, and that preferentially removes a light isotope. Molybdenum in the Black Sea, however, because you are feeding in this open ocean water that is isotopically heavy and then almost quantitatively removing it and putting it in the sediment, the Black Sea has organic rich sediments that are the same or almost the same isotope composition as the open ocean, right? So you're feeding in molybdate ion that has been made heavy in the oxic open ocean because manganese oxides are removing light molybdenum. You're feeding that molybdenum-rich water into the Black Sea, and then you're quantitatively removing the molybdenum. So you record the open ocean isotope composition, even though the Black Sea is itself not the place where that heavy molybdenum is being produced. It's recording that heavy molybdenum if there's quantitative removal, which there isn't always, but in the, it's close. Now, so those are the two sedimentary sinks of molybdenum so far. The open ocean oxic sink, manganese oxides, the euxinic sink or the sulfidic sink in places like the Black Sea. There is another one, and this occurs in the open ocean as well, but not in the open ocean, not out here where manganese oxides are dominant. It occurs at upwelling margins like the west coast of Africa and the west coast of South America. Here, we have a lot of productivity in the surface ocean, a lot of export of organic material into the deep ocean. The deep ocean gets very close to anoxia and actually periodically is anoxic here because of the respiration of all that organic matter that's produced up here. But it doesn't quite get anoxic normally. But what happens in these regions is that you have a sediment water interface here. You have high molybdenum concentrations in the water column. because it's still mostly oxic. But because of all the organic matter you're burying in the sediment, the pore waters very quickly become sulfidic. And schematically, what happens is the sulfide diffuses up down this concentration gradient. The molybdenum diffuses in from the water column, and you get sulfide formed here where the two diffusion profiles meet. At least this is a schematic view of what happens. And there is molybdenum removal from the water column, but it happens sort of at depth in the sediment, and you have to diffuse the molybdenum into the sulfide that's just beneath the sediment-water interface. Now, so what I've told you so far, I'm going to sum up here in terms of a mass balance of molybdenum isotopes in the ocean. So modern rivers are about this. This is molybdenum, delta 98 molybdenum. Modern rivers are about here. The modern oceans are much heavier than those modern rivers, as I've told you, the dissolved pool. The main reason for that is the fact that the oxic sink, manganese oxides in the open ocean are removing very light molybdenum. But that is complicated by the fact that there are two other sinks. There's a Oceanic sink in the Black Sea, and there's this upwelling ocean margin sink, which is rather large, in fact, and seems to remove a molybdenum of intermediate composition. So there are three sinks and one input. And if the oceans are in steady state, these equations should be true. The isotopic composition of the input should be partitioned between these three different sinks. So the size of the oxic sink times its isotope composition plus the size of the Oceanic sink times its isotope composition plus the size of the upwelling sink times its isotope composition should add up to the input if the oceans are in steady state. And just to, I know this is maybe a little bit unfamiliar to many of you, but just to give you an analogy, this is exactly the same way in which people use carbon isotopes. You know, the main input of carbon isotopes to the surface of the Earth is from the mantle. Its isotope composition in del13C is -5 per mil. And that input is partitioned into two outputs, into carbonate sediments and into organic carbon-rich sediments. These are produced by photosynthesis, or ultimately, mostly by photosynthesis, and there's a big carbon isotope fractionation. So you end up partitioning this input into two sinks, and the two sinks must add up to the input if the ocean is to be in steady state. Now, so we tried to use this some years ago to go back in Earth history. And then this is a complicated diagram, so let me just go through it a little bit slowly. What it shows is time here, present day back to 3.5 billion years. Here's molybdenum concentrations in ocean sediments first. Now what this shows is that, as I told you earlier, back here, molybdenum concentrations in ocean sediments were low because there wasn't much molybdenum in the ocean, because the oxidative weathering source of molybdenum to the ocean was small, because we didn't have an oxic atmosphere. When we get to this period of time, molybdenum concentrations can be high. They often aren't. If we're in an open ocean situation, they'll be low, but if we're in a Black Sea situation, they'll be high. You built up a reservoir of molybdenum in the ocean that can be taken out in Black Sea type situations, so you can get high concentrations. Now, then if you look at the isotopes, again, the data is messy, but there's one important thing I want you to notice here, and that is, all the way through Earth history, there was never a time when the oceans had any sediment forming that was as heavy in molybdenum isotopes as today, until the early Cambrian. The early Cambrian, if you believe this data set, and if you believe we're not missing data, say here, which we could be, it could be a missing important data here, there are sediments in the early Cambrian for the first time that have the modern molybdenum isotope composition. Now, there are sediments that are lighter as well. There have to be, there always is, but we don't know of any process that makes a sediment that is heavier than the modern ocean. So what this is suggesting then is that molybdenum isotopes became as heavy in the modern ocean as today for the first time in the early Cambrian. And today they're this heavy because we have a manganese oxide sink that is removing the light isotopes from the ocean. And we suggested that this may be interesting because this, of course, is the time when you had this massive, remember again, so the modern oceans are heavy because you have this oxic sink only, really. I mean, this might make them heavy as well, but, well, no, it doesn't. This is the thing that makes them heavy because this is the one that is lighter than the input and therefore driving the dissolve phase heavy. So we said, look, this is interesting because the early Cambrian is when you had the first massive radiation of animal life that desperately needs oxygen in order to respire food. Okay, so that's molybdenum, and you can argue with that conclusion, but the observation that this is the first time we see heavy molybdenum isotopes in the ocean is there, and the first time we see a modern-like ocean in terms of molybdenum isotopes. And that modern-like ocean is completely controlled by this manganese oxide sink. Now, I want to move on finally then to another isotope system, and that is nickel. Now, what I'm going to tell you now is much newer. This is something that we've been working on much more recently, but it turns out to be a similar story in some ways to molybdenum. So nickel is a transition metal as well. We, mostly us, there are a few other papers just coming now, but mostly us have been measuring the dissolved pool of the oceans. For the nickel isotope composition expressed as delta 60 nickel, which is the 60-58 ratio relative to a standard as usual. And what we see in the water column is two things. Here are the data for the Pacific, the Atlantic, the Indian Ocean. We see two important features. The first one is there is variation in nickel isotopes in the water column in the top 500 meters at low latitudes only. Now, that's a really interesting observation that I'm not going to talk about today. What I'm going to focus on today, again, is the fact, just like molybdenum, that the deep ocean, most of the ocean, in fact, is isotopically, well, everything is isotopically heavy relative to the inputs and also relative to rocks, just like molybdenum. Oh, sorry, 2 minutes. I'm very sorry. Okay, so we have these heavy isotope compositions relative to the input, which is again like molybdenum. Now, why? Again, we saw with molybdenum that is controlled by the manganese oxide sink, removing light molybdenum. Is it the same for nickel? Okay, so we've been looking at the sinks of nickel from the ocean, which one of them is isotopically light and which one of them is making the oceans heavy. We've looked at upwelling margins, just like molybdenum. So these are places like the Peru and the Namibian margin. What we see there is sediments that have lots and lots of nickel. That nickel is really strongly correlated with the organic carbon content of the sediment, right? So it's really been taken up into cells, apparently, and then buried as organic matter. But the isotopic composition of that nickel is the same as the modern ocean. It's not fractionated from the modern ocean. This is an important output flux of nickel from the modern ocean, but it's not the thing that's making the oceans heavy. It's not isotopically light and therefore pushing the oceans heavy. Then when we go to the open ocean, we see something completely different. When we go look at sediments in the open ocean, the oxic sink, what we see is there is not much organic carbon in those sediments. There's lots of manganese, though, in those sediments. These are manganese oxide rich. Now, I just want to show you how closely nickel is associated with manganese oxide. First, I'm just going to show you data from ferromanganese crusts and nodules, and you see that if you plot manganese versus nickel concentrations, there's a really strong correlation. Well, given the nature of these sediments, it's really quite a strong correlation. There isn't a correlation with iron. The nickel is apparently associated with manganese in these manganese oxide sediments. So what we've done then is to go to the open ocean, to the Eastern Pacific, and to look at these manganese oxide. These are not crusts, right? These are not crusts. These are just sediments that have a lot of manganese oxide in them, but they've got lots of other stuff in them too. And so in order to be sure that when we measure these sediments, when we look at them, that we're really looking at nickel associated with manganese, because there's lots of other stuff in these sediments as well, we plotted the manganese versus nickel concentrations, and you see that there's a good correlation between the two, and the ratio of nickel to manganese is very similar to crusts and nodules. When we measure the isotope composition of the nickel in those manganese oxide-rich sediments, what we get is this. We get a very light isotope composition, much lighter than seawater, which is this blue line. There have been some experiments, just like molybdenum, absorbing nickel to manganese oxides. The experiments show that the nickel sorbed to manganese oxides is light, right? However, it's much lighter, in fact, than we observe in these manganese oxide-rich sediments for reasons that we don't completely understand. Okay, and so that's two sinks we have so far, the upwelling sink and the manganese oxide sink in the open ocean. Again, there's a sink in places like the Black Sea that are to do with sulfide. I'm not going to go into this in detail, but what I just want to tell you is that this sink is small. It's really very small, and it is slightly lighter than what we see in sediment is slightly lighter than the open ocean in nickel isotopes. There's complicated things going on in the water column which are interesting, but I don't want to go into. But the ultimate sedimentary sink is really controlled by this, by sulfidation of the nickel, which makes this species that is very insoluble, just like molybdenum. But the removal of nickel is not at all quantitative like it is with molybdenum. It's only a little bit of the nickel removed. We know there's an isotope fractionation from calculations between this species and this one, and it matches the difference between the open ocean and the sediment, so that's okay. Right, so again, we have this budget, exactly the same process as with molybdenum. We have these three sinks. They're in different places isotopically for nickel. They're different sizes versus molybdenum. But again, the important thing is that rivers are here, the main source of nickel. The oceans are here, and the reason the oceans are heavy is nearly all to do with the output of light nickel to manganese-rich sediment. We've only done some measurements so far in the Eastern Pacific, but again, it's the same as nickel, right? That the same as molybdenum. We have a heavy ocean relative to the inputs, and it's due to the output to this oxic manganese oxide-rich sink. And again, you can write the mass balance equation saying the three outputs, when you add them up, must add up to the input. I haven't said anything so far, by the way, about why modern rivers are not the same as the continental crust, because that's another thing that is important here. Why the oceans are different from rivers, the input, but rivers themselves are different from the continental crust. Why is that? Well, I'm not going to go into this in detail, but we've done a lot of studies on this, most recently in the Amazon. And what we found is that the main control on the molybdenum and nickel isotope composition in rivers, in the dissolve phase of rivers, is also retention of light isotopes in soils. And soil studies have sort of confirmed this, at least for nickel, that light isotopes are retained in soils. The heavy isotopes go into the river, and it seems to be oxides, again, that are retaining the light isotopes in the soils. Okay, so then just to finish, we wanted to look into Earth history for nickel isotopes as well. And this is something we've absolutely just started. This is not published, and it's been done by this student, Sun-Ming Zhao. And so what he did was, we said, okay, look, we want to get the past ocean. We want to get the isotope composition of the past ocean. We should go and look for upwelling organic rich sediments in the geological record. Now, that's what he did. He tried to find organic rich sediments in the geological record. The problem is that when we're working on the past, we never know whether organic rich sediments that we find are from upwelling margins. And that's what we need. That's where nickel organic rich sediments record the open ocean nickel isotope composition. We need those sediments. But what we observe in the record is organic rich sediments. And so he's measured lots of these organic rich sediments, and that's the blue data versus nickel compared to the modern Peru and Namibian margins. There is more scatter in the geological record data, and there's an indication that the slope might be bigger than for the modern margins, but that's what he finds. What we would like to do is to filter this data to make sure that these samples that we're looking at are really from upwelling margins, not from other places where you get organic carbon-rich sediments. And so what we've done there is, I don't want to go into the details here, but other previous workers have used certain trace metal ratios in organic rich sediments, looking at them today to say which of them are from upwelling margins and what are characteristics of those upwelling margin sediments that we don't find in other places. And what they've discovered is that, for reasons I won't go into, is that if the cadmium molybdenum ratio of the sediments are high, and if the cobalt to manganese ratio is low, that is telling you that organic rich sediments are from upwelling margins and not from some other geographic setting. And so what Sun Mingxiao did was to say, I'm going to filter this data set and I'm going to get rid of all the samples that don't fall in this top left quadrant with high cadmium molybdenum and low cobalt manganese, because those are the ones that we think today are from upwelling margins, and so maybe in the past are. So we're left with this bunch of data here, and then he measured the nickel isotopes of those. And remember, the hypothesis is that nickel isotopes in these sediments should be recording the past ocean. And here's what he gets. This is very preliminary, and I literally just plotted this up yesterday, right? So here's what he gets. Here's time along the x-axis. It's a log scale because we have a lot of data to show. Here's nickel isotopes in these sediments. Here's the modern input to the oceans. Here's rocks. Here is the modern ocean. And remember, this modern ocean is heavier than the input because the manganese oxide sink is removing light nickel. At face value, what these data are telling us is that the first time the oceans become heavier than the modern input is only 100 million years ago. That is really late. That was unexpected to me, because this means that there was not a prominent manganese oxide sink until this time, and then we start to get heavier values, and it's really late. But what I just want to show you, so here, there's the Cenozoic, the beginning of the Cenozoic, and we might just at the end of the Mesozoic begin to see the nickel isotope composition of the ocean get higher than the input, suggesting that there's something removing light isotopes. Now, this is just a piece of fun. I'm not making a firm conclusion here, but I showed you this iodine calcium data earlier, and I showed you that there were still things going on in iodine calcium very late. And it is sort of interesting that there are patterns here in the nickel isotope data that are kind of reminiscent of what we see in the iodine calcium data. So we see apparently nickel isotopes like the modern ocean here when iodine calcium ratios are high. We see low values in the Mesozoic when iodine calcium ratios are low. We see high values in the middle Paleozoic when iodine calcium ratios are high, etc. There may be some corroborative evidence that things are happening really late here. Now, but we have a problem here, because I told you earlier that molybdenum isotopes controlled by the same manganese oxide sink emerge from their Precambrian kind of values in the Cambrian. We appear to have a strong manganese oxide sink controlling molybdenum isotopes in the Cambrian, but we don't see the effect of that sink for nickel until the late Mesozoic and the early Cenozoic. Why is this? This is a problem, but maybe it's a problem that if we solved, we would learn something from it. And I'm going to finish here by trying to give you one clue as to why there might be a problem here with nickel isotopes. That is maybe why it's responding really late in the oceans relative to some other things. So this is the budget I showed you earlier for nickel isotopes. And so we again have this manganese-rich sediment in the Eastern Pacific, which is really light, which we are saying is pushing the oceans heavy. Now, when we first tried to quantify the nickel budget for the oceans, we didn't go and look for these manganese-rich sediments. What we did first was to measure ferromanganese. We didn't do it, someone else did, but we used their data. Ferromanganese crusts. Now, ferromanganese crusts are different from manganese-rich sediments in that they sit at the sediment-water interface. They are not very much diagenetically altered because they're not buried in sediment and there's no organic carbon in them to fuel diagenetic reactions. They just sit on the surface. Whereas the nickel and these manganese-rich sediments in the East Pacific are buried with organic carbon, there's manganese mobility, there's all kinds of further diagenetic reactions going on. When we measured ferromanganese crusts, though, when someone else measured them, what we find is these things, they're not isotopically light. Ferromanganese crusts, in fact, are slightly heavier than the modern ocean. And this initially puzzled us because this mass balance doesn't work, right? You have sinks, huge sinks that are heavier or the same as the modern ocean, but very little that's light, and this mass balance just doesn't work. And we were puzzled about this for a long time because the only measurements we had of manganese-rich sediments, but I think they are telling us something that's wrong, that in fact that this is the right picture. We should be going. It's a much bigger sink than crusts in terms of its size. We should be going to these manganese-rich sediments, not ferromanganese crusts, to get the isotopic composition of the nickel that's leaving the ocean into the manganese oxide sink. This is something that's just a hypothesis. The minute we think this might be what's going on here. Here's a water column, here's sediment. Manganese oxide with sorbed nickel is coming out of the water column all the time in oxic situations. Some of it's ending up in ferromanganese crusts, usually where there's no other sedimentation going on. And that just happens. They just sit there and you get no diagenesis. But the stuff that ends up in the sediment is undergoing diagenetic change because there's organic carbon. And then that's probably retaining the light nickel, whereas there's a heavy nickel backflux into the deep ocean. And there are reasons. I'm not going to go into this because I'm running out of time. There's the reasons why this diagenetic transformation might be happening that we know about. I'm going to skip over the last few slides because again I've run out of time, and just finish here and say we are learning some things from trace metal isotopes on the Phanerozoic ocean. They are largely controlled by manganese oxides, by this redox couple, but we're being told contradictory things at the minute by different isotope systems and different elements. And if we could somehow combine the different constraints that we're getting from the different elements so that we have a multi-dimensional view of different elements, then we would learn something important. And that's what I want to do next, is to try and resolve these discrepancies that we're seeing between these different isotope systems. Thank you. And that's it.
Thank you, Professor Drake, for such an informative talk. And personally, I'm very happy to see you in PRL virtually, again after 3 years. I'm sure we'll be loaded. Hope to see you again in PRL, yeah, personally. I'm sure we'll be loaded by very interesting questions, which will open up a great discussion. But before I take up questions from the YouTube, I would request members joining us on WebEx to kindly come ahead for discussion. So, Gyana, would you like to start?
Thank you. Thank you, Professor Vance. This was really a nice overview of ozone redox state and its impact of trace metals. I have a couple of questions. One of it is for the first part of the atmospheric oxygenation, where you mentioned about sulfide oxidation. This sulfide oxidation is likely to act as a sink of atmospheric oxygen also, and also a source for CO2. So if it is starting as a feedback for increase in oxygen, there is a likelihood that subsequently it can have a decline in the oxygen, but we don't see that. Can you, what could be a possible reason for this?
So you're talking about sulfide oxidation on
Right.
the continents by oxidative
Yeah.
weathering. Yes. So for sure, once that starts operating, once we have an oxic atmosphere and that starts operating, that could indeed cause a decline in atmospheric oxygen again. And today we think today the calculations that people have done suggest that the sinks of oxygen from the modern atmosphere are about 2/3. About 1/3 reaction with reductants from the mantle, so reducing gases from the mantle, and about 2/3 are via oxidative weathering, like that one of those reactions I showed you. But you see, the thing is, this probably operates a bit like a negative feedback, because that's a big sink of oxygen today, because oxidative weathering is important because we have a lot of oxygen in the atmosphere. When we have no oxygen in the atmosphere, that reaction doesn't happen at all, and therefore it will not be a sink at all. When we have low amounts of oxygen, it will be a small sink, but not as big a sink as today. So it may be actually that weathering, oxidative weathering, removal of oxygen acts a bit like a feedback, in that the rate at which it happens is itself proportional to the amount of O2 in the atmosphere.
Okay.
You see?
Yeah, got it. Yeah. So my second question was about this manganese sink that has a molybdenum and nickel impact. But the iron isotope also is likely to show some of these signatures, because the oxic sink may influence also iron in some way. So
Yes.
we have a quite steady iron isotopic ratio for last 1 billion year or so. So do you think there is a mismatch between molybdenum, nickel, and iron isotope?
So the problem with iron, and one of the reasons I've kind of stayed away from iron isotopes myself, I've done a little bit, but is that iron is really complicated in general, in the oceans, at the Earth's surface. So in the oceans, for example, iron is very strongly complexed in solution, and that creates isotopic effects. There is, of course, so the advantage of things like molybdenum and nickel is they do not have an oxidation state change themselves, right? And that means, so the biggest iron isotope effect that we see is with the oxidation state change between iron 2 and iron 3. And then there's organic complexants in the modern ocean that also have the complexed iron has a different isotope composition from the non-complexed iron. And so there's a lot going on with iron. Then there's burial of pyrite, which is very isotopically light. And so there's a lot of processes that influence iron and its isotopes that I think make it certainly interesting, but hard to deconvolve all those different processes. But it's another one that it provides constraints. It's just that I'm not sure how to deconvolve all those different processes that control iron isotopes.
Great. Yeah, thank you. Thank you very much for this discussion.
Professor Sonal Singh had a question for you.
Thank you very much, Jiti. And thank you very much once for providing a fantastic talk, right from beginning origin of Earth and evolution of oxygen and its impact on chemistry and evolution of life, I think, and finally giving the contemporary ocean chemistry. I think it was fantastic. I think at the end we should have expanded a little bit because time was not less. So I think we missed a little bit, but I think that's fine. I have one or two questions regarding first part. When you are talking about evolution of oxygen, is a titration between source and sink of oxygen. So first of all, when we are talking about source, the photosynthesis, so my question is very basic. What makes this blue algae to start the photosynthesis, which was not there earlier?
Well, so the first thing to say is that oxygenic photosynthesis was almost certainly not the first form of photosynthesis that occurred, right? So people use phylogenetic trees and molecular clocks to try and understand the evolution of these early microbial metabolisms on Earth. And the first forms of photosynthesis, according to those phylogenetic trees, did not involve oxygen as the oxidant. So, for example, it did not involve oxygen as the product and did not involve water as the reductant. So, for example, there's a metabolism that is well known whereby H2S is used instead of H2O as the reductant, and the byproduct of that is sulfur, not oxygen. Obviously, you use the hydrogen to combine with the carbon. There's a well-known metabolism that uses reduced iron to combine with organic carbon, and the reduced iron is the reductant. That does not produce oxygen, that produces oxidized iron. And so why the reasons why microbes and blue-green algae or cyanobacteria evolved to use oxygen is something that I do not know the details of, or to produce oxygen, to use water and to produce oxygen. I don't know the details of. Of course, it's evolutionary favorable. There is lots of water around, right? Much more water than there is H2S and reduced iron. In another sense, it's evolutionary unfavorable because, as you know, oxygenic photosynthesis produces these very strong oxidants that organic matter hates, right? As it's a toxic thing for them. But it is more efficient at harvesting light than the other forms of photosynthesis, the anoxigenic forms of photosynthesis that we know about. But you'd have to talk to a molecular biologist to really understand why it evolved in the first place, how it evolved in the first place.
And you mentioned, or means we know that deeper oxygen was oxygenated quite late. So do you think means the global ocean circulation which oxygenate today, it was not efficient enough? Or do you think the consumption was much more because iron was there, zinc was there, iron was getting oxidized, and organic matter was getting oxidized? So it was a complex scenario, but whether it was means the whole ocean circulation was sluggish or it was more material to oxidize?
Okay, that's a trick. That's a difficult question, right? But I can tell you what you know this, but I can tell the audience what the three main controls are on deep ocean oxygen, right? It's the extent of how much there is in the atmosphere. So the surface ocean, if it's fully chemically equilibrated with the atmosphere, will have what Henry's law dictates how much O2 will dissolve in the surface ocean. Then, of course, yes, it's the circulation, the physical circulation that brings the oxygen down to depth. So you do need that. Now, that is controlled by tectonics to some extent, right? It's, in a way, the pattern of circulation we have on Earth is an accident of tectonics. But it's also controlled by how warm the surface is, because the warmer the surface is, the more stratified the ocean is, right? So you have less density-induced overturn. Warmth also controls how much oxygen you dissolve in the surface water. And then it's also controlled by the biological pump. right? Because if you have big phytoplankton, like we have diatoms today, they will be exported a long way down into the deep ocean, perhaps even to the sediment, and you may bypass respiration in the water column to some extent, or you may cause respiration in the deep ocean. Whereas if you have a phytoplankton ecology that's dominated by small organisms like cyanobacteria, you may have an oxygen respiration that's very localized in the intermediate ocean or even the surface ocean. So yes, it depends on the physical circulation, but it depends on other things too. And because the physical circulation is something that we don't know much about in the Cambrian, right? We just don't know much about it in the Cambrian. People have tended to emphasize other things like the kind of phytoplankton that are around and to what extent, to how strong the biological pump is. Of course, the other thing is how much nutrient you're putting in the ocean, how strong chemical weathering is on the continents and supplying phosphorus to the ocean. Another thing that you might expect to be stronger in warm conditions on the Earth. So there are lots of controls. Physical circulation is certainly one of them, but not the only one.
Okay, so the last question, I will not take much time. The last part, anyway, it was very interesting about your correlation of manganese, nickel, and molybdenum. Only means we are also working on molybdenum, and but this when we are talking about oxic zinc and anoxic zinc, so you know oxic zinc, lighter molybdenum is going, anoxic zinc, it is as it is eugenic condition, as it is molybdenum is going as seawater. But when we are talking about this anoxic or suboxic, where you are referring to this upwelling area 1.6 or 1.5, whatever that. So what is the factor which is controlling this fractionation? Is it is a mixture of these two, or something else is happening?
So I have a theory about this, but it's my theory, and not everyone agrees with me, right? So I think what's going on here. So we know that when you transform molybdate to tetrathiomolybdate, the fully sulfidized species, that occurs when you have lots of sulfide above a certain threshold value. And if you quantitatively transform molybdate, the oxidized form, to the sulfidized form, it is, and you quantitatively extract that molybdenum, put it in the sediment, then the sediment records seawater. However, we know also, we've done experiments, and there are ab initio calculations that show that the process of transforming molybdate to the fully sulfidized species goes through 4 steps. The stepwise replacement of those oxygens by sulfur, and each step involves an isotope fractionation. And if you only do it partly, you are going, and the sulfidized species are progressively lighter. Each time you put in a sulfur for an oxygen, you get a lighter species. Now, if you completely transform it to tetrathiomolybdate, then obviously there's no isotope fractionation. But if you only half do it, then you are going to express an isotope fractionation. And I think that's what's going on at these intermediate situations. And that's that cartoon I showed you with molybdate diffusing down and sulfide diffusing up. That is a situation where you are going to get maybe only partial transformation of the molybdate into thiomolybdate. And I think that might be what's going on, but I have not proven that yet. I would like to one day, but.
Okay, thank you very much. Thanks a lot.
So Dr. Valiur Rahman.
Hi, Direk. This is Valiur. I met you, if you remember.
Oh, hello.
Hi.
Hello. Of course, I know your papers.
If you remember, there I gave a talk on molybdenum history. Yeah. So nice to see you after almost 8 years now. Okay. Okay. Coming to the question that you talked about, the inconsistency between the nickel and the molybdenum records. So the partly that inconsistency, I would say, yeah. So it's coming from because of their the fractionation and their pathways. So the molybdenum, if you see, it's a anoxic. The sulfatic condition, almost there is no fractionation. Whereas in the manganese zinc removal, that pathways you have a 2.7 per mil fractionation. Whereas in nickel, it's all along in the entire range from the oxic to the sulfatic condition, all along there is a fractionation.
Well, yes, that's true, but when we measured those different sinks, we see quite distinct values for the nickel isotope composition. When we had, so what's really, really startling about nickel is that if you go to an upwelling margin, like I showed you with Peru and Namibia, there's no manganese in those sediments, and nickel is completely associated with organic matter, nothing else. Really clear, one process. And then you go to the open ocean, what you see is nickel is really clearly associated with manganese oxide. We have not found an intermediate situation yet. So we've not found situations that are between those two. Then there's except for the Black Sea, which is intermediate in terms of the isotope fractionation you see, but it's not intermediate in terms of process. But I think overall, what you're hinting at in your question is basically right. There are ways to reconcile these things, but the problem is so far that we and other people too have just looked at one element and said, oh, look, there's something happening here. Isn't this exciting? Look, molybdenum is changing just when animals are evolving. Isn't that interesting? Or someone else goes to another place and does something different, a different element. And what I'm saying is that no one so far has attempted to look at multiple isotope systems, see if they find different things, and then interrogate those discrepancies to see what it's really telling us. And, you know, basically you're right. There are almost certainly reasons why it's telling us something different. What I'm more interested in is what exactly those reasons are and what they tell us about Earth history, really.
Okay, thank you.
Dr. Vineet Kuswami?
You're muted, I think.
Yeah. So I have just a couple of questions. So one of them is that it has already been shown by your work initially that molybdenum isotopic composition of riverine water is much heavier than the crust or whatever is the supply is heavier relatively to what people thought earlier, and it largely can be attributed to the formation of interaction with the ferromanganese oxyhydroxides in soil or in the, but then this lighter isotopes or lighter pool of isotope is also carried to the ocean. And then because we did some of the work in the margin sediments, margin area of the Bay of Bengal, and we see that molybdenum isotopic composition is really lighter, which could be because of this light pool coming from the riverine discharge, and it could undergo dissolution under low oxygen conditions. And I think it could also be the case for nickel and other isotopic systematics. So I would like to know your comments on this one.
No, I'm sure you're right. I'm sure that's correct. We don't, so I'll tell you, I think you are absolutely right, and this is potentially important. But so I'll tell what we know where we've studied rivers in detail. So we studied the Amazon. We had a paper last year, on a detailed study of the Amazon basin. And what we did there was to measure the molybdenum isotope composition of different rivers in the Amazon basin, and we measured the amount of molybdenum in particulates and compared it with the amount of molybdenum in the dissolved load. And what we found is, and we measured the size of the particulate load as well. So at least for the Amazon, now the Amazon is not deposited on a shelf that then becomes anoxic, but what we see for the Amazon is that the particulate load of rivers is absolutely tiny compared to the dissolved load of rivers. Mm-hmm. So Yes, you can, and I'm sure you do remobilize the molybdenum, the light molybdenum from the particulates in certain situations. But for that one big river, if you say how much dissolved molybdenum is delivered to the ocean and how much particulate molybdenum, 98% of it is dissolved. Now you can mobilize that 2% of solid molybdenum, and that's fine, but it won't have much impact, at least in that case, right? It will, even if you mobilize all of it, it would not have much impact on the oceans because there's just too little molybdenum in the solid load. Now, I'm not saying that that is always the case, but that's the observation that we made in the Amazon. That's the first thing. I'm sure there are rivers where that's not true, where the particulate load is big, and therefore if you mobilize it, you'll see the impact in the oceans. The other thing is, if in the end, the molybdenum and nickel that is delivered to the ocean is not heavy, like we see in the dissolved load of rivers, and it's in the end, it's the same as the rocks, right? In the end, that what you get because you remobilize the light from particulates in the ocean, and that actually it doesn't matter what happens in the dissolved load of rivers. Ultimately, you still have to have a source from the continents. And if the dissolved load of rivers is not heavy, and if you are remobilizing the particulate light, then you should get the continental crust in the oceans. That makes the problem of the oceans being heavy worse. Right? The fact that the oceans are heavy, then it's still you still have to have something removing the light isotopes. And if the riverine delivery is really 0 per mil or something for molybdenum, once you take account of the process that you've observed, then you still have this, it's still the same. It's quantitatively different. Of course, the mass balance will not behave in quite the same way. Do you see what I'm saying?
Yes, I get it. Yeah.
So I mean, what the weathering does apparently is partition molybdenum into a heavy dissolved phase and a light particulate phase. Now in the Amazon, that particulate phase is tiny. And even if you remobilize all of it on the shelf, you would not see it in the ocean. In your case, you do see it, and therefore you are adding back the particulate to the dissolved load, and you should maybe in the end have a molybdenum entering the ocean. Overall, that's the same as rocks, but you still have then the same pattern. You still have to remove light isotopes to explain the modern ocean.
Yeah.
And actually, it's worse.
Yes, and I think it's to do with the particulate load, because for some of the rivers like Ganga and Brahmaputra, the particulate load is enormous. It's like it's enormous. For Yangtze and the other rivers, it's enormous. So I think it cannot be applied means you have to see where the particulate load is enormous, and it could possibly impact the dissolved load by remobilization. Okay.
Right.
Yeah.
And so the conservative thing to do is to say that the overall riverine load is somewhere between the dissolved load and 0 for molybdenum, right? In terms of its isotopes, right?
Yes. Okay. Yeah. Thank you very much for answering that question.
So another question from Dr. Namandeep Singh.
Yeah. Thank you. Thank you, Professor Vance. It was a very informative and exciting talk. I surely can say that I've learned a lot of things from this talk. So I had 2 questions, but one has already been taken in the panel, which deal with the influence of physical circulation controlling the deep water oxygenation. I had that question. And the other one was when you talked about there's a phase in the history when you see molybdenum isotopic composition going above the present day ocean water isotopic composition. So I wanted to understand, I mean, I didn't get it totally. So were you talking about the impact of bioaccumulation or bioassimilation in that time period? Because molybdenum is a bioessential nutrient, so but generally it is present in very high concentration, so it is not biolimiting, I guess. So, but at that time period, does the biology played a role in controlling that? I was not clear. So can you just again explain?
No, all I'm saying is, and hello, by the way, I remember meeting you when I was in Ahmedabad too. or maybe it was in the NIO. Now I can't remember. It was on that trip anyway. And so, what I'm saying is, if we look at the geological record and we measure molybdenum isotopes in all sediments in the geological record, they vary a lot, but the first time we see heavy values like in the dissolved phase of the ocean today, the first time we see that is in the early Cambrian. Now, today, the reason why the ocean has heavy isotopes in the dissolved phase is because manganese oxides are removing the light isotope. And you make manganese oxides in the ocean if the ocean has oxygen to oxidize manganese, to make it manganese oxide. Now, it's interesting that the first time that we see that heavy value that characterizes the modern ocean, the first time we see it is in the early Cambrian. That suggests to me that that manganese oxide sink, removing the light isotopes, was there for the first time. It wasn't there before, but it was there afterwards, making molybdenum heavy in the ocean, and therefore we see it for the first time in a sediment. Now, it's interesting then that that is also the time when animal life first appeared, because that people think that that might have been caused by a rise in the amount of dissolved oxygen in the ocean. And the two things may be correlated, they may not be correlated, but they appear to happen at the same time. Now, you're right that molybdenum is bioactive. I did not talk about that today because for today, for example, even though molybdenum is required in enzymes, it has no impact on the water column molybdenum concentration that in any place that I know of. It's required, but there's so much molybdenum in the ocean that it doesn't make any impact on the dissolved concentration. Is that okay? That answer
Yeah,
the question?
thanks. Clarify.
So I don't see any hand raised in the WebEx among us, our WebEx members. Is there anyone who would like to ask questions? If not, I'll move to YouTube questions. So there are a few questions here. One by Dr. Srinivas. He's asking, what about nickel isotopic composition of manganese nodules crust? If we take molybdenum isotope mass balance, can we assume manganese nodules crust accumulating from early Cambrian?
Yes, I think to make the early Cambrian isotopically heavy, as we see in the record, something must have been removing light molybdenum and some kind of manganese oxides, whether it ends up in the sediment as a nodule or a crust or dispersed in some way throughout the sediment, some formation of manganese oxide must have been happening.
Thanks. Another question is from Rahman. He is saying, what are your views on the MOE, that is Mesoproterozoic oxygenation event?
I don't know much about it. So there are, my personal view here about what and I'm including myself in this. This is a criticism, and I'm including myself in this criticism, is that too often in the past, we have all gone and measured stuff in the rock record, one isotope system or one element, and we found something. And often we don't understand the modern cycles well enough to be completely sure about what is controlling that signal that we see. And I think sometimes that has resulted in statements about the geological record that are not as robust as maybe they could be. And I include, the statement that we made about molybdenum in the Cambrian. It could be that's wrong. And, the nickel isotope stuff doesn't agree with it. And what we need to do more, right, is combine these
multi-isotopic technique kind of.
huh?
Multi-isotopic technique kind of.
Exactly. But it's not easy, because finding the right rocks to measure these things on in the past is not easy.
I guess. Okay, there's another question from Neeraj Rastogi. He wants to understand, to understand GOE, you talked about variability in 34 sulfur and 13 carbon. Why did the isotopic composition of oxygen not studied directly? It might give you more direct evidences about sources, processes, those affected oxygen concentration level, isn't it?
So it is actually being studied directly now. This is something I don't know much about, but people are using triple oxygen. So not just Del 18O, but 16, 17, 18 in the rock record to understand the history of oxygen. Now, as I don't know much about this, but as I understand, apparently ozone formation causes mass-independent fractionation of oxygen isotopes. And and you only get ozone formation if you have O2. And so people are trying to use triple oxygen isotopes in records of the Earth's surface to do this, but I'm afraid it's not something I know much about.
Okay, thank you, Professor Derek. And that's all the question I can see on the YouTube chat. And with this,
it was quite a lot of questions.
Yes,
I'm glad there are no more.
I'm sure there would have been more discussion if you were here.
Can you allow me to also ask one question, Kuljit?
Oh, yes, Professor Anil Bharadwaj.
It was very illuminating for me actually to hear to your very interesting talk. And my very simple question is that right in the beginning you were talking about, oxygen sudden enhancement somewhere around 2.2, 2.4 billion years back. And before that, you are also showing that it was constant going back up to 4 billion. So how do we know about this oxygen level down to 4 million years back? What is the source for that?
So mostly this comes from the quantitative constraint, mostly comes from something called mass-independent fractionation of sulfur isotopes. So the source of sulfur to the atmosphere right through Earth history was volcanism, and it was emitted either as SO2 or H2S. And in the modern atmosphere, there are, and actually in the atmosphere through Earth history, that sulfur can be transformed into other forms of sulfur, to elemental sulfur, to different forms of oxidized sulfur, to different forms of reduced sulfur. Now, we know from experiments that those transformations cause mass-independent fractionations of sulfur isotopes, right? And what people have observed is that those mass-independent fractionations are seen in sediments formed in the ocean before 2.4 billion years, and after 2.4 billion years, they disappear. So that appears to be telling us that we didn't have these transformations of sulfur in the atmosphere. Now, to do those transformations, you need UV light in the troposphere. And so one thing it might be telling is that there was no more UV light in the troposphere after 2.4 billion years, so we didn't get these transformations of sulfur. The other thing it might be telling us is that when we have an oxic atmosphere like today, those transformations are happening, but the species that you make, the reduced species, are really short-lived. And basically everything in our oxic atmosphere is completely transformed to the most oxidized form of sulfur, sulfate. And that completely eliminates these mass-independent fractionations. So, and people have done some modeling to show that if oxygen levels get above 10 to the minus 5 present levels, you will eliminate those mass independent fractionations of sulfur that we see before 2.4 billion years and not afterwards. That is the main constraint on, and we see them in ocean sediments, right? In the rock record preserved in ocean sediments.
So what I'm trying to still look at, how do we know that it is 4.5 billion or 4 billion or 3 billion year old stuff we are looking at?
Well, we have sediments, we have rocks preserved from 4 billion years ago, where we can measure, which have sulfur in them, that were formed as chemical sediments in the ocean, and sample the ocean. And the ocean is in equilibrium with the atmosphere. And therefore, if you believe the measurements that you make on those chemical sediments precipitated from the ocean, and if you believe they are telling you about the past chemistry and isotope geochemistry of the oceans, then you can make some inference about what that ocean looked like and what the atmosphere in equilibrium with that ocean looked like. Do you see what I mean?
I was looking at, how do you date?
Oh, date. Oh, so a
age.
variety of, okay. Oh, the sediments are dated in a variety of ways, using radiogenic isotopes. You can date black shales with rhenium osmium isotopes. You can date carbonates with uranium lead. Often you have volcanic events in between the sediments where you can date the volcanic event, and therefore it tells you what age the sediment is. Does that answer your? Okay.
Right. Okay, good. Thank you.
So let me invite my colleague, Dr. Durga Prasad, to formally thank and conclude this session.
Thank you, Professor Kuljit. So it's a nice duty to deliver a word of thanks. So on behalf of the Director PRL and our Vyakhyaan committee and entire PRL family, I thank Professor Derek Vance for accepting our invitation and delivering our 27th Vyakhyaan of this series. Thank you very much, sir, for accepting our invitation and delivering an enthralling Vyakhyaan on the oxygenation history of our Earth, and also elucidating on various geochemical tools, process, and proxies that are paving a way to this understanding. Also, many thanks for patiently answering all the questions from our viewers, both from YouTube and WebEx platform. I thank our director, Professor Anil Bhardwaj, for his continued encouragement and support, which made us to take this Vyakhyaan series further ahead. I thank our professor, our dean, Professor Pallam Raju, Professor Nandita, chair, and Dr. Lokesh, co-chair, and all the members of Amrut Vyakhyaan committee, and all others behind for their efforts. Particularly, many thanks go to our participants and viewers on WebEx as well as YouTube who have joined us today for this Vyakhyaan. With this, we come to the end of this episode. Now it's time to say goodbye for today from PRL. So we will be back next week almost at the same time with another interesting Vyakhyaan. Till then, stay tuned and keep following us and PRL updates. Thank you very much.
Thank you.